Hello guys, I am Vaishali Kikan and we are discussing the organic chemistry. So today we are going to start our discussion from the stereoisomers. What are the stereoisomers? Stereoisomers are the compounds having the same structural formula, that is, atoms are joined in the same way, having the same connectivity, but atoms are arranged differently in space. If I look at atoms in the space, so the atoms are arranged differently. So now coming to the isomers. Isomers can be defined as the structural isomers and the stereoisomers. We had already discussed about the structural isomers. Now coming to the stereoisomers. There are two types of stereoisomers, configurational isomers and conformational isomers. Now the configurational isomers are cis-trans isomers, which are also known as E or Z isomers. Then we have the optical isomers. So we are going to talk about both of them, cis-trans isomers as well as the optical isomers. So now what are the cis-trans isomers? Which are having the same structural formula but group are arranged differently in space, right? So we have the different arrangement in space. So let's understand how we have the different arrangement in cis isomer as well as trans isomer. So we have the different compound over here. First is 1-bromo-but-1-ene. So yes, it is having the cis-trans isomers. The cis isomers will be having the two hydrogens at the two carbons in the same direction, and now bromine is the another group and CH2, CH3 is the another group which are in the same direction, right? Then in the trans isomer we have the bromine and CH3, CH2 in the another directions. They are in the opposite directions, and two hydrogens are also in the opposite direction in the trans isomers. So you can see these are the two groups that are connected in the same direction, and here they are connected in the opposite direction in the trans isomer. 2-bromo-but-1-ene, it is not having any cis-trans isomer. Why? Because here if I change even the position of these HH and these Br and CH2, CH3, then also I will be getting the same structure, right? So I will be getting H carbon, double bond carbon, Br, CH2, CH3. So this is the same structure. In the front of CH2, CH3 I have hydrogen, in the front of bromine I have hydrogen. But here in the front of bromine, here we have CH2, CH3. But here in the trans isomer, in the front of bromine we have hydrogen. In the front of CH2, CH3 I have bromine. In the front of CH2, CH3 now we have hydrogen. So even if I change the configuration, then also I am getting the same structure. So it is not having cis-trans isomers. Coming to the 3-methyl-pent-2-ene, it is yes having cis and trans isomers. So here we have CH3 both connected in the same direction. Here we have H and CH2, CH3 connected to C double bond C. So here if I change the structure, now here if I take the CH3 group upside and CH2, CH3 downside, in the front of H we now have CH3. Previously in the front of H we had CH2, CH3. In the front of CH3 we had CH3. Now we have CH2, CH3 in the front of CH3. Now coming to the 2-methyl-pent-2-ene. No, it is not having the cis-trans isomers, because here you can see here we are not having any structure which can be made in the terms of the two different groups, right? So here we have C connected to 3 hydrogens. Even if I change the configuration, there is no change. Here the C is connected to CH3. So now here C is connected to 2 CH3 over here. C, CH3 connected to CH3. Now here we have double bond which is connected to H and connected to CH2, CH3. So now here two of the groups are same, right? So two of the groups are same which are on the same carbon. At this condition we will not be having the cis-trans isomers. Here also we have 2-methyl group, but those are there on the different carbon, so I had the cis-trans group. Coming to the optical isomers. So what are the optical isomerism? It is another type of stereoisomerism. So here we have the optical isomerism that we are going to discuss. Here we have the mirror image structures. With the mirror image structures which are non-superimposable are the optical isomers. So here let's take the example of butane to all. So this is the structure of butane to all. The carbon will be having the tetrahedral structure. So at one side CH3 is connected, at the outside OH is connected, at inside H is connected, and here C2H5 is connected. Now if I take the mirror image, outside we have OH, inside we have H, upside we have CH3, but from the left C2H5 has moved to the right. So now this is a mirror image molecule which are non-superimposable. If I want to superimpose it over this structure, C2H5 here is in right, here it is in left. So these are non-superimposable. So these are optical isomers. But if I see the butane, in the case of butane, here we have CH3HH C2H5. Here we have CH3HH C2H5. So here we have only one form of butane here, because here we have two hydrogens connected, right? In the previous case, what I had, in the previous case we had the two different OH and H were connected, right? So two different groups were connected to the carbon, due to which the mirror images were non-superimposable. Here the mirror images are superimposable, so these are not as the optical isomers. Now coming to the chiral center. What are the chiral center, or you call it as the chiral center as well? So the carbon atom with four different group attached to it is the chiral center, right? So here if you see this structure, in this structure, if I see the first carbon, here we have two hydrogen, these two are same, so this is not chiral. So here if I see this second carbon, in the second carbon, here we have carbon, here also we have carbon. So same structure, same atom are connected, so this is also not chiral. If I see the third carbon, here we have CH2 connected, here we have OH connected, here we have hydrogen connected, here we have CH3 connected. All four are different, so it is chiral center. Coming to this structure, if I see this carbon, three hydrogens are connected which are same. If I see this carbon, two carbons are connected which are same. If I see this carbon, so here at this carbons, here we have CH, CH3, CH3, right? And here we have OH, CH3, here we have CH, CH2, CH3. So all four are different. At this carbon, I can say this carbon is my chiral center. If I see this carbon, two hydrogens are same, so not chiral. So now coming to this structure, if I see this carbon, two chlorine are same, not chiral. If I see this structure, here we are connected with CCl2Br. Right, here we are connected to Cl, H and Br. So all four are different. So this is a chiral center. Now again, if I see over here, we are connected with CH3. We are connected with C double bond OH. Here we are connected with H. Here we are connected with NH2. So this is my chiral center. Now coming to the next structure here. Here we have two chiral centers. Here, if I see the first carbon, here we have three hydrogens connected, not a chiral center. Here, if I see this, here we have CH3, here OH, here H, here CHOH, CH3 connected. So now here if I see this carbon, here we have CHOH, CH3, and here we have OH, H and CH3. So this is again a chiral center. You have to see all of the four connections. So here first is this, second is this, third is this, and fourth is this. So all four are different. I can say this carbon atom is a chiral center. Again, if I see this, we have here at this carbon we have two hydrogen, not chiral. We have two hydrogen, not chiral. Here also we have two hydrogen, not chiral. If I see this carbon, hydrogen, CH3, different, right? Here we have CHOH, CH2OH. CH2OH is different. Now here we have CH2, CH2, CH3. So this is also different. So this is, we have as the chiral center. So whenever we have the chiral centers, there would be an optical isomer of that compound, right? So you have to look for the chiral center. If you find out the chiral center, you will say yes, it will be having the optical isomers. Now coming to the molecules that do not exhibit the optical isomerism when we are not having the chiral center. So here you can see the two chlorines are connected to the carbon. Here the two bromines are connected to the carbon, no optical isomerism. Here the two hydrogens are connected, three hydrogens are same, no optical isomerism. Right, so here we have the connection of CH3 and here also we have CH3 group, so no optical isomerism. Here at this carbon we have a double bond OH, and now the double bond O structure will not tell me that this is two bonds are connected to O, so this is again not a chiral center. So here you can see two hydrogens same, two hydrogens same. Now here we have the connection with CH3 and CH3. Right, so again here two hydrogens same. So all of these are not chiral centers. So here we have two hydrogen, this carbon is not chiral. If I see this carbon, here we have double bond with C, two bonds are connected with the carbon only. So this is not chiral. So here if I see this, again two double bond C is there. So it is not a chiral center. So if I see this structure, 2 hydrogen are present here, 3 hydrogen are present. So all of them are not chiral. So optical isomerism will not be there. These are not the optical isomers. Now coming to the three-dimensional representation of the optical isomers that are showing 2 pair of mirror images. Right, so here you can see this is the first structure, C double bond O, C double bond O, OH, and here we have C, H, OH, CH3. Right, if I see the mirror image, if I see this carbon is my chiral center, the chiral center will be having H, OH, CH3 and C double bond O, OH group present to it. So now here if I take the mirror image will be having C double bond O, OH, C, H. Now here we have OH and CH3. So now I can say these two are mirror images and these two are different compounds which cannot superimpose on each other. These are optical isomers. Similarly, if I see these two, here we have C2H5, here we have hydrogen, bromine, CH3. So all of them are different. If I take its mirror image, we have bromine, CH3, C2H5H over here. So now these two are mirror images, these two are optical isomers. Now if a molecule has plane of symmetry, so if I have a round molecule, cyclic molecule, and if it has the plane of symmetry, then it will not exhibit the optical isomerism. So now here we have C, ClH, C, HH, C, ClH, C, HH. So now if you see this line, if I cut it from this line, so we will be having the same structures here and here. Right, so here we will be having C double bond H connected, here also we have C double bond H connected, right? So it's the plane of symmetry is there, so these are not optically active. Here also if you see, if I cut these structures from here, so this structure is similar to this structure, right? So these are symmetric, these two structures are symmetric, so obviously I have a plane of symmetry, so they are not optically active. Now if I see this structure, there is no plane of symmetry in this structure. So here we have C, ClH, C, ClH, here we have C, ClH, but here we have CHH. So if here I had C, ClH, so that time I had the plane of symmetry and it was not optically active. But here we have C connected with 2H, here C is connected with Cl and H. So we cannot cut it into two symmetric planes. So now no plane of symmetry optically active. Now coming to this structure, here we have C, ClH, CHH, CHH, CHH. So now here also I will be getting the, so here we will be having Cl, right? So now here I can say this is again having the plane of symmetry, not optically active. Now if I see this structure will be having a double bond, and due to which I can see, if I see over here we have chlorine, hydrogen, and in the below structure I will have only hydrogen. So even the double bond is present and only one chlorine is present, so I cannot cut it into two equal halves. So no plane of symmetry, this is optically active. I hope you understood the various things that I have discussed in this video. Thank you so much.